For our last problem, we're going to look at a situation where we have multiple bodies or multiple blocks that are being accelerated. This is similar to our lab where we had a cart on the table and we were using masses off the edge of the table to accelerate them. When we want to take a look at a situation like this, we're going to need to draw a free body diagram for each of the situations. So here we have a lovely problem. A 3-kilogram block is resting on a table, attached by string to a 5-kilogram block off the edge. So let's draw a free body diagram for each one. This will be block A. This is going to be block B. For block A, we have the force normal, force of gravity, and tension. Overall, this block is going to accelerate to the right because it only has tension acting on it to the right, and it's not going to be accelerating up or down. It's just getting dragged along the table. For block B, we're going to see over here that we have the tension force going up and the force of gravity pulling down. It's going to be accelerating downwards because gravity is going to win over tension because this block is larger than this block. Okay, so when we have that all kind of figured out, we want to set up an equation for each block. Now we have to ask ourselves, which direction do we want to look at? For block A, we're focusing on the x direction because the x direction is where this block is going to have movement. So our x direction for block A, we're going to say that the net force is going to equal simply tension. There's nothing else acting on it in the x direction. So the mass of block B or A times its acceleration is going to equal tension, or 3 kilograms times A equals T. Now over here for block B, we only want to focus in the y direction because that's the only way that we have problems or that we have forces acting on it. I'm going to say that down is positive and up is negative because it's accelerating downwards. So my net force on block B here is going to equal the force of gravity minus tension, or I could write this out as mass of block B times acceleration equals mass of block B times 9.8 minus tension. Okay, let's fill in these numbers. We would have 5 kg times A equaling 5 kg times 9.8 minus T. All right, not too bad. Now, let me ask you this. Are the accelerations of block A and block B going to be the same? Well, you're right, Alec. Yes, they will, because they are connected. We can't have one accelerating faster than the other when they are attached together. What about the tensions? Is the tension in the string here going to equal the tension in the string there? Right again. Yes, it will. Because it's the same string, it will have the same tension. So now, I see I have 2 equations and 2 unknowns. We can easily solve for acceleration and for tension by substituting things in. What I'm going to do here is I'm going to take tension and say that that equals the same thing as 3 kilograms times A. Plug that in over here. When I do that, I'm going to end up with 5 kilograms times A equaling 4.9 newtons. I just took my 5 kilograms times 9.8 and subtracted out 3 kilograms times A. I'll add this over. 8A will equal 4.9 newtons, and A should equal, oh, sorry, this isn't 4.9, it's 49 newtons. And A should equal 6.